Welcome to chapter 29. We're going to do a very brief introduction to quantum physics. So quantum physics is all about looking at things on a very small scale. We're talking about electrons and protons and things of that nature. So very small scale, the little bits and pieces and parts that make up the bigger pieces and parts. So it starts out talking about the discovery of the electron. I think all of quantum physics begins there. Thomson's credited with the discovery of the electron. He used what's called a cathode ray tube. That's the same sort of thing as old-fashioned TVs. You remember the big wide ones before everything was a flat screen. The electrons came off and there was a glow at the other end, and we were able to determine that that beam that was produced could be deflected or moved with an external magnetic field. And it led people to think, well, then this beam is made out of smaller things that are influenced by that magnetic field. So Thomson was able to measure the ratio of the mass of the particle, the charge of the particle, excuse me, to its mass. We refer to that as E over M, and come up with a number that was consistent. Millikan is famous for his oil drop experiment, where he was able to quantize or give a number to the charge on the electron. So if we take a little brief look at just this little drawing of what the oil drop experiment involved. So you have a device to create oil drops. You can see it looks a lot like an old-fashioned perfume bottle. It is. It's an atomizer. So you have these little tiny oil drops. They pick up an electric charge, and as they fall between these charged plates, you're able to change the rate that they fall at by changing the charges on the plates. Because you remember that opposites attract and likes repel. So you can alter the charge on the plates, and that's going to alter how strongly it either attracts or repels the charges that are on the oil drop. After tediously measuring these charges over time, Millikan and his team of graduate students were able to come up with a value for the charge on the electron. And since it's 1.6 times 10 to the minus 19 coulombs, that's a pretty impressive feat. Oh, I overshot again. I seem to do that, don't I? So with Planck's quantum hypothesis, he was able to notice that objects emit radiation with an intensity that is proportional to the fourth power of their Kelvin temperature. So as the temperature increases, the electromagnetic radiation shows an increase in frequency. I don't seem to be really good at this scrolling, do I? So the end result was that Maxwell explained that the radiation comes about because those electric charges are oscillating or moving. You think about rubbing your hands together, and if you do that, the friction creates some heat energy there. So Maxwell extrapolated that to thinking about oscillations in electric charges, that if they vibrate, then perhaps some sort of radiation could be produced. His curve to predict the intensity as a function of wavelength and the actual curve are shown here below. You can see we've got three curves. We've got the Rayleigh-Jeans curve, we've got the Planck curve, and we've got the Wayne curve. And the Wayne and the Planck agree strongly. The Rayleigh-Jeans, well, it's a little just crazy when we look at it. So the curve's been drawn for something called black body radiation. A black body is a non-reflecting surface. So that means that it will absorb all the radiation that strikes it. Your black body temperature is going to increase, and as it increases, the black body will emit radiation at a higher and higher frequency. And if the frequency goes up, the wavelength comes down. As the frequency goes up, the wavelength comes down. So the temperature is related to the wavelength by this equation. It's called Wayne's law. So it's lambda sub P multiplied by T is equal to 2.90 times 10 to the minus third meter degree Kelvin. And if we look at an example of this, you'll hopefully see why we care about it. So the light emitted from the sun has a wavelength, that would be its wavelength of propagation, lambda sub P. Its wavelength is approximately 500 nanometers. So that allows us to get a temperature approximation for the sun. We plug in the to solve for T, it would be that 2.9 times 10 to the minus 3 divided by the wavelength. So 2.9 times 10 to the minus 3 meters degree Kelvin divided by that 500 nanometers. So 500 times 10 to the minus 9 meters. And it gives us a temperature of 5.8 times 10 to the third Kelvin, which is hot. So Wayne's law helps us to understand why stars have different colors. Remember that each color has a different corresponding wavelength. So temperature and wavelength are linked. That means temperature and color are going to be linked. Red happens to give you a cooler temperature than blue does. I know that seems counterintuitive, but if you've ever seen a flame, the hotter the flame, the bluer it gets. So probably not candles in your experience, but other things, maybe a torch for welding. So there is a problem with our Rayleigh-Jeans curve, and that's something called the ultraviolet catastrophe. You may have noticed it was the curve that shot straight up. With that particular one, an object would have to glow blue and its theoretical curve would go to infinity in the ultraviolet range. So that's one of the reasons we discount it. Max Planck developed a quantum hypothesis in an effort to describe black body radiation. The only way he could do it is if he thought of the energy as being broken up into discrete packets or quanta. So rather than being continuous with any number possible, just like charge is broken up into discrete packets of 1.6 times 10 to the minus 19 coulombs, Planck said energy is broken up into these little individual packets, and they're equal to h multiplied by the frequency. So h is something new. It's called Planck's constant, and it's 6.626 times 10 to the minus 34 joule seconds. So the minimum amount of energy possible is equal to h multiplied by the frequency that we're looking at. And remember, frequency and wavelength are related to each other. C equals lambda f. So lambda is the wavelength and f is the frequency. And c is the speed of light in a vacuum, 3 times 10 to the 8th meters per second. So this means that the energy of any molecular vibration can be thought of as some multiple of that minimum energy. And so this is what's referred to as Planck's quantum hypothesis, that energy is not continuous, but it's broken down into little packets. You may remember that charge is broken into those little packets that we refer to as 1.6 times 10 to the minus 19 coulombs. So let's look at some theories and see how they support this quantum hypothesis. And one is the photon theory of light and the photoelectric effect. Einstein used the quantum hypothesis to argue that when light's emitted, it's going to do so in packets or quanta. We refer to those as photons. So rather than being continuous, light comes in little bursts, at least in our viewpoint. And those little bursts are photons. And again, the energy is equal to H multiplied by the frequency of the light. So the photoelectric effect also supports a quantum theory of light. In the photoelectric effect, light will shine on a metal surface, and if it's the appropriate frequency, electrons will be ejected. So if you have light in the 700 nanometer range, that's in the red range, and it strikes a potassium surface, it's not going to have enough energy to push out electrons, so you won't get an electron ejected. But if you're in the 550 nanometer range, that's a green, you will have enough energy and you'll have electrons ejected traveling at this rate. If you are in the 400 nanometer range, you can have electrons ejected in this range. So depending on the frequency of the incoming light, that's going to determine the exit energy for these electrons that are forced out of the surface in the photoelectric effect. So the kinetic energy of the emitted electrons is directly related to the frequency of the incident light. And that leads us to say, well, in this instance, light is acting like a particle. If light acted like a wave, the intensity of the light would be corresponding to the height of the wave, the frequency would correspond to the number of waves, and the energy of the emitted electrons would have to be directly proportional to the intensity. But in reality, the intensity of the light corresponds to the size of our particle. The frequency of light corresponds to the number of particles, and the energy of the emitted electron is going to be directly proportional to the frequency, which it is. So in the photoelectric effect, light acts like a particle. And remember, when we say light acts like a particle or light acts like a wave, we're just using these as descriptors, as ways to describe this sort of thing. All right, so I'm muddling along. Let's see what else we've got going on. The Compton effect also, oh, I'm sorry, I forgot to mention that in the photoelectric effect, we use it like for light meters or the electric eyes or smoke detectors. There are all kinds of ways to open a door. Sometimes they use pressure pads. Sometimes they use electric sensors that just break a connection. There are a variety of things, but smoke detectors do use this photoelectric effect. All right. So the Compton effect also supports the photon theory of light. In the Compton effect, an X-ray, which is a photon, strikes the surface and bounces off of an electron. So here's our incoming X-ray. Here's that electron minding its own business. When the X-ray strikes the electron, the X-ray bounces off and the electron also moves off. You can think of it as a little bit like two pool balls hitting each other. So the electron recoils off and goes over this way. The photon or X-ray recoils off. But the funny thing is that the wavelength of the recoil photon is different from the wavelength of the incident photon. And that end result, again, supports our particle theory of light. So we also want to talk about photon interactions and pair production, and I just sort of whizzed right by that. So when a photon, remember that could be X-rays or visible light or things of that nature, passes through matter, it interacts with the atoms and the electrons in one of four ways. It'll either interact by the Compton effect, the photoelectric effect, or the photons could knock electrons up to a higher energy state. And then when they fall back down, usually the energy is released as visible light. Or you could have something called pair production. So that happens in the presence of a large nucleus where you've got a photon forming a positive electron and a negative electron, and they travel off. An interesting thing is that the reverse of pair production is annihilation. You've got a positron and an electron coming together, and when they meet, they are no longer particles, but they give off the energy. So in this little graphic, the top one shows annihilation, where a positive electron, which is a positron, and a regular electron come together and annihilate each other, and just the energy is released in the form of a photon. And the bottom one shows pair production, where two photons come together and the energy is converted to mass in the form of a positron coming off and an electron coming off. So what does that leave us with? That leaves us with something called the wave-particle duality. We think that light acts both like a wave and a particle, that in some experiments you can explain it as acting like a wave. In some you explain it as acting like a particle. Niels Bohr proposed what's called the principle of complementarity to explain all this dual nature. He said to understand any given experiment, so any one experiment, you can use the wave or the photon theory, but he said you can't use both at the same time. You can't use both to explain a single experiment. You have to pick. Well, if light can act like a wave and a particle, what about particles? Do they actually have a wave nature? Louis de Broglie said they did, and that the wavelength of a particle, like an electron, would be given by lambda equals h divided by the product m times v. Remember, mass times velocity is the momentum. So if you take Planck's constant and divide it by the momentum of your particle, you're going to get the wavelength. Just to give you some sort of example, if you had a 200-gram ball traveling at 15 meters per second, it would have a teensy wavelength of 2.2 times 10 to the minus 34 meters. If you have an electron moving at 5.9 times 10 to the 6 meters per second, its wavelength would be 1.2 times 10 to the minus 10th meters. So big difference if you're talking about something as big as a ball or as small as an electron. And in fact, Davidson and Germer performed an experiment that scattered electrons off the surface of a metal and showed peaks consistent with wavelengths that were predicted by the de Broglie formula. So our conclusion is that while things like light have a wave-particle duality, physical particles can also have a wave-particle duality. So just a little teeny bit about quantum mechanics. Back in the last century, they began to suggest that atomic particles were also wave-like in nature, and things that have waves move in a fashion that's best predicted by probabilities rather than absolutes. So Schrodinger is famous for coming up with an equation to describe this wave nature. The wave function is a probability distribution. So think back to your discussion, maybe in chemistry, of the electron distribution around an atom. You don't talk about an electron being in a specific place at a specific time. You talk about it being in these regions of space. And so these probabilities say that in that region, you have a much higher probability of locating the electron than you do in a different region. So the Schrodinger equations used to find the allowed energy levels for quantum mechanical systems. And remember, quantum are just little particles, so protons, electrons, little things. So the wave function gives you the probability of finding your particle at a particular location. And again, this is only appropriate on an atomic level. So our Schrodinger wave equation is a basic equation that describes non-relativistic material particles and relates the probability of finding the particle to the square of the wave function. The wave function is usually symbolized by the Greek letter psi. That's this little pitchfork looking symbol. And the probability is the square of it. So psi squared, we refer to it, we don't say psi multiplied by psi, but they use this little asterisk to indicate that you're squaring it. And it's read as psi star psi. So you move along that way. You can't talk about quantum mechanics without discussing the Heisenberg uncertainty principle. So the Heisenberg uncertainty principle says that it's impossible to make a measurement on an object without disturbing it. And so Heisenberg said you can either know the position of the object or the momentum of the object, but you don't get to know both at the same time. So you discuss probabilities. So the Heisenberg uncertainty principle tells you that you can either measure the position or the momentum, but you can't measure both at the same time for an object. So you can't make a measurement without disturbing it. So we only discuss probabilities when we look at the Heisenberg uncertainty principle. Again, you can measure either the position or the momentum, but not both simultaneously. And this stops our discussion of chapter 29. So we will stop the share and stop the recording.